Number 24. Explain in terms of figure 21.2 how unstable heavy nuclides, which have an atomic number of greater than 83, may decompose to form nuclides of greater stability if A, if they are below the band of stability, and B, if they are above the band of stability. Okay, so here is that figure 21.2. This is basically the band of stability diagram that you've probably seen in your class, right? There's three different types of lines generally here. There's this black line, which represents that you have a 1-to-1 neutron to proton ratio. Now, usually in this question, we're going to be talking about NP ratios, right? So just know that this black line represents a 1-to-1 NP ratio, which means that for as many numbers of neutrons that you have, so that's what the N stands for, you have a neutron, you should have the same amount of protons. So basically, this is a slope of 1. So 5 for 5, 6 for 6, 7 for 7. It's a 1-to-1 ratio. So just know that ratios, right, are those two dots, but just know that ratios are division, right? It's a fraction. So we're going to be talking a lot about NP ratios here. Just know that an NP ratio, because, it does come out to be a general number, just know that your NP ratio will basically be your number of neutrons divided by the number of protons. So anytime, this is good skill to know, that anytime that you're dealing with the ratio and they say something dot dot something, right, that first thing is always the numerator. So since it's an NP ratio and the N came first, the neutrons have to be in the numerator. And then your P came last, so the protons have to be in the denominator. And when you take your neutrons and divide it by your protons, you should get some type of decimal value. But if you have, 5 neutrons and 5 protons and you divide them, you should get a number of 1, right? So an NP ratio, if dividing, you're just going to get the number 1. So that's this black line. Now, the band of stability is the blue kind of like staircase that climbs up. Now, just know that in the band of stability, so this blue is the band of stability. This is where all of your stable isotopes are, stability. As we can see here, there are very, very few stable isotopes in this world, and there's a lot of green. The green represents unstable or radioactive material. Now, as we see here, as we have, down in the bottom, that band of stability, the blue, overlaps with the black line, which means that generally our stable atoms are going to have a 1-to-1 ratio, right? A 1-to-1 N to P ratio. But as we climb up the mountain, right, as we increase our number of protons, we increase our atomic number, the band of stability actually strays away from a 1 N to P ratio. And as you climb higher and higher and higher, the N to P ratio naturally gets larger and larger. But we're not talking about, big numbers. We're talking about maybe this ratio down here would be like 1.25, then it's like 1.4, and then it's like 1.5. So we're still in the 1 and change type of idea. And once again, those numbers are if you take the total number of neutrons the atom has and divide it by the protons. So now, we have to find out how unstable heavy nuclides are going to become stable if they're below the band of stability. So we are in the green region that is below the band of stability. All right, so maybe, generally speaking, it's going to be the green that's below the band of stability. So let's just write this down here. So, this is not, there we go. So below the band of stability. So, in general, right, so since you are below, that means naturally you have an N to P ratio So if you divided any isotopes that are down here, if you divided their number of neutrons by number of protons, you should get a number that is lower than normal. Okay. And that's why it's below the band of stability. Now on the flip side, let's just do the flip side first, just so that we, our understanding is complete, right? We have things that are above the band of stability. It's all the green that is above that line, right? And, once again, this is just like a general understanding here, that we are above the band of stability. So what do you think that means in terms of the N to P ratio? Should we be below the number of stability, or what's going on with that ratio? Yeah, the N to P ratio, if we took all these isotopes, took their neutrons divided by their number of protons, the N to P ratio would be higher than what it should be. Okay, so there's the issue. In general, right, if you have a lower N to P ratio, if you're below the band of stability, which is letter A, so maybe I'll say low N to P ratio, that means that in order to become stable, you need to increase the value. We need to increase this ratio to become stable, or, more stable. So there's only two types of radioactive, I guess we'll say, decomp forms of radioactivity that can increase this N to P ratio. So the first one is positron emission. So we'll say positron emission. Positron emission. So that means that you are emitting a positron. A positron is the anti of an electron. So it's a 0 on the top, but a +1 on the bottom, if we were doing nuclide notation. And it's a beta because it's basically an electron, but a positive form of an electron. So you could either emit a positron, which means that you would be, releasing a positron in the atmosphere, or the second thing you could do is you can do the opposite, and you can capture an electron. So they call it electron capture. Electron is the beta, so we still put a B here for beta, and the true form of an electron is the -1 and the 0 up on the top. Both of these will allow you to increase your N to P ratio, and then you would be closer to the band of stability. Now, for letter B, what about if you were above the band of stability? Well, that means that, originally your N to P ratio, the number of neutrons to proton, is way high. So what we have to do is we need to lower this ratio. And it turns out that there are two forms to doing that. So there's 2 for the top and 2 for the bottom. So we'll do that this way. And these are your other 2 emissions. So there's basically 3 emission types and 1 capture type. The other 2 emissions are the full-blown beta emission. So that's the electron. So beta emission. A beta is just an electron, so, we'll just say B, 0, and -1. I don't know why they don't say beta capture, but, generally this is the same thing, but, usually they'll say it's electron capture. And then the last one is the alpha emission. So you got beta emission, and you got alpha emission. This is where you're going to be releasing a helium ion. So He4 on the top, 2 on the bottom. And there you go. So these are your 2 different types. So if you're below the band of stability. Low entropy ratio, you'll either withhold, you'll take an electron, you'll capture it, or you'll release a positron, and that way your entropy ratio will increase. On the flip side, if you're above the band of stability and you need to bring it down, you'll do beta emission, so you'll release an electron in the atmosphere, or you'll release a helium, and either one of them will do the trick. So, yay! I hope this helped. Thank you for viewing the video. Subscribe to the channel if you want to help us out. If you haven't subscribed yet, thank you so much. I hope you're having a great day. Keep studying hard. We got memberships on the channel if you want to become a member. Woot woot. But I'll talk to you soon, okay? All right, bye-bye.